In this video lesson, we're going to talk about enthalpy. Up until now, we've been referring to heat in one type of way. If you remember back 2 video lessons ago when we talked about energy, we said that heat could be represented with the letter Q. However, the second way it could be represented was with the letter H, and H in this case stands for enthalpy. Please note that enthalpy is the exact same thing as heat. So really, enthalpy is nothing new that we haven't already known. Only this time, we're just giving it a specific name. The reason why we do this is because now we're going to talk about the heat that is involved in a chemical reaction or process. Now notice right below. Below it says that reactions of substances will either absorb energy or release energy. If they absorb or release energy, that changes the sign of delta H, or in other words, change in heat. If delta H is positive, that means that the heat increased, which must mean that heat was absorbed and therefore makes it endothermic. On the other hand, if delta H is negative, that must mean that the heat decreased, meaning it must have released or lost energy, therefore making it exothermic. Now, when we talk about enthalpy regarding equations or chemical equations, it's important to cover something called a thermochemical equation. If you look at the prefix thermo, thermo means heat, and therefore a thermochemical equation is simply an equation that includes the heat exchange involved in the reaction. Let's take a look at 2 examples of thermochemical equations written below. In the first one, we see the synthesis of iron 3 oxide. Notice that in this reaction, it's balanced, it has reactants and products, and it has states of matter. S's stand for solid, whereas G's stand for gas. All of this is review. This is what would be in a chemical equation. However, there's one additional piece of information on the right-hand side. Notice the delta H. In this reaction, the delta H is negative 1,625 kilojoules. By having this heat exchange represented in the equation, this is therefore known as a thermochemical equation. Now notice the sign of delta H. It is negative. What kind of reaction would that make this? The answer is an exothermic reaction. Therefore, we can deduce that when we make iron 3 oxide, 1,625 kilojoules must be released. In the second one, we see another example of a thermochemical equation. Notice the delta H in this case, 33.2 kilojoules. Since it is positive, we can know that this reaction must be endothermic. In other words, heat is required to make this reaction happen. Now there's multiple ways that you can actually write out a thermochemical equation. This is the first way that we saw on the previous slide. But there's also another way that we can write it. Let's think about this. We know from the previous slide that this was an exothermic reaction, since it's negative. If heat is being released in this process, would heat be a product or to be a reactant? The answer is it would be a product. The reaction between these two things has to happen first, and as a result, it makes the product and energy. That's why energy is released. Since then it is an exothermic reaction and heat is a product, heat can also be written as a product on the right-hand side. If you were given this reaction, you would know it was exothermic because the heat energy is written on the product side. Let's take a look at the other example we had. We had that the heat exchange was 33.2 kilojoules. Since it's positive, we know that this was an endothermic reaction. And in endothermic reactions, heat must be added to the reactants before anything will happen. And therefore, heat is written as a reactant on the left side. It is important to know that both ways are correct. Either way is fine, but make sure you're familiar with both types of thermochemical equations. Here's another way you can think about it that will help you out. Imagine the chemical equation as a tunnel. And in that tunnel, everything enters from the left side and exits on the right side. If the reaction is endothermic, it must enter on this side, therefore being on the reactant side. However, if the reaction is an exothermic reaction, it must exit on the product side, meaning that the energy will be written on the product side. Just a little trick to help you out. Now that you know that, go ahead and take a look at this example. What I'd like you to do is pause the video and do your best to write out this thermochemical equation written below, with symbols, states of matter, and balanced. When you're ready, go ahead and click play and I'll reveal the answer. The answer to this one, written correctly with all chemicals balanced and states of matter, would be written as so. 2H2, it's in the gas form, plus oxygen, written in the gas form, makes water in the liquid form plus 44.2 kilojoules, since the energy is released. Another way is doing delta H with a negative 44.2 kilojoules. Both ways are correct. Now that we know what a thermochemical equation is and how to write one, let's go ahead and move on to another property of enthalpy. There are three types of molar enthalpy that we're going to discuss. The reason why it is called molar enthalpy is it's always in relation to 1 mole. Let's look at the first one. The first one is called delta H COMB. COMB stands for combustion. And what that is the heat that is released from the burning of 1 mole of a substance. Let's go and look at this table. Let's look at sucrose. Sucrose is the first one, or table sugar. If you had 1 mole of table sugar and wanted to completely combust it, it would take 5,644 kilojoules to do it. Let's take a look at glucose. Let's say you had 1 mole of glucose. How much energy would it take to completely combust it? The answer is 2,808 kilojoules. Now notice all of these signs are negative. Since all the signs are negative, we know that this is all exothermic, meaning all of that energy is completely released when combustion happens. All right, that was our first one. Let's look at the second one. The second type of enthalpy is what is called delta H vap, or heat of vaporization. Heat of vaporization is the heat required to vaporize 1 mole of a substance. Remember, vaporization is going from liquid to gas. Since heat is required in this process, we know that this is going to be an endothermic reaction, as opposed to combustion, where it was an exothermic reaction, because heat was released. Let's look at another example to understand heat of vaporization. Notice in this table it gives you 5 compounds: water, ethanol, methanol, acetic acid, and ammonia. It gives you your formulas, and in the next column it gives you your delta H of vaporization in kilojoules per mole. First, notice that it's all positive. Positive 40.7, 38.6, 35.2, and so on. Because they're positive, I know that this is going to be an endothermic reaction. And that makes sense, because to vaporize anything from liquid to gas, you have to put in energy. Now let's take a look at water. Suppose I gave you exactly 1 mole of water and asked you how much energy it would take in order to vaporize it. Well, I know according to this chart that it takes 40.7 kilojoules of energy for every 1 mole. Now let's think about this. If it takes 40.7 kilojoules to vaporize liquid to gas, how much energy do you think then would be released if I went the other direction, gas to liquid? The answer to that is it would be the exact same amount, but opposite. It would be negative because it's losing energy. And that's a key point. Please go back to your notes, and next to heat of vaporization, also write down / condensation. If it takes 40.7 kilojoules of energy to vaporize 1 mole of water, it must lose 40.7 kilojoules to condense water. The final one is delta H of FUS, or fusion. Please know that fusion is just another term or word for melting. The definition of delta H of fusion is it's the heat required to melt 1 mole of a substance from solid to liquid. Just like before, the opposite works as well. Opposite of melting is freezing, and therefore the number would be the same, but just the sign would be opposite. So let's go back to our chart. All right, let's look at water. Suppose I gave you 1 mole of water in the solid phase, and I wanted you to melt it into the liquid phase. How much energy would be required? We know that for every 1 mole of water, it takes 6.01 kilojoules of energy to melt 1 mole of water. What if you wanted to go the opposite way? What if you had 1 mole of liquid water and you wanted to freeze that mole? Well, it would lose 6.01 kilojoules. In other words, it would be negative. So you see, it's the sign of the enthalpy that tells you in which direction you're going. Let's look at this pictorially. Here is water. Notice I give you water in 3 states. I give it to you in the solid form, in the liquid form, and then in the gas form. Let's assume that we have 1 mole of this water. First of all, let's say you wanted to melt that 1 mole of water from solid to liquid. It takes 6.01 kilojoules of energy to do that. Suppose you wanted to keep going and vaporize that 1 mole of water from liquid to gas. It takes 40.7 kilojoules of energy to do that. Anytime you're moving towards the gas phase, it needs energy and therefore is endothermic or positive. However, let's say you wanted to reverse that process. You wanted to go take that 1 mole of water from the gas phase down to the liquid phase. You would have to remove energy, and specifically, you'd have to remove that 40.7 kilojoules, which is why it's negative. And all the way back down from liquid to solid, you'd have to remove the 6.01 kilojoules of energy. Since energy is being removed, this is exothermic, which is the reason why the sign of the numbers are negative. Now that we have an understanding of these 3 types of enthalpies, let's go ahead and solve this problem. Feel free to go back in the slides to go to those charts or use your textbook on page 529 and 530. All right, the first question is this. How much heat is released if 2.43 moles of sucrose are burned? Since molar enthalpies are always in relation to moles, we always want to make sure that the information is given to us in moles. If it's not, we need to convert. Luckily, in this example, it gives us 2.43 moles of sucrose. We don't have to convert anything from grams to moles, it's already in moles. And so I'm going to write that out. 2.43 moles of sucrose. All right, now that I'm in moles, I want to convert those moles into energy. Since sucrose is being burned, I know that I'm going to be using the delta H of combustion. So let's go ahead and go back to that chart and look at sucrose. According to sucrose, for every 1 mole burned, it's going to release 5,644 kilojoules of energy. So I use that value and plug it in. For every 1 mole, it releases 5,644 kilojoules. Moles cancels out, and our answer will be in kilojoules. Now all we have to do is just multiply through. 2.43 times negative 5,644. With the correct number of sig figs, our answer is approximately negative 13,700 kilojoules. Remember, I need to have the negative because energy is being released. Let's do one more together, and then I'll let you do one on your own. Go ahead and try this one. If you'd like, pause the video and try to work it out on your own. Otherwise, watch me work it out right now. The question says, how many grams of glucose must have been burned to release negative 9,389 kilojoules of energy? All right, the process is still going to be the same, but now we're going from a different direction. We're going from energy to amount rather than amount to energy. The process, however, still remains the same. Always write out what you're given. I was given negative 9,389 kilojoules. Right away, I know that this is an exothermic reaction because it released that energy. All right, I need to somehow convert energy into an amount or moles. Since glucose was burned, I know once again I'm looking at delta H of combustion. So let's go ahead and go back to that chart and find glucose. For every 1 mole of glucose burned, 2,808 kilojoules of energy is released. So knowing that, I'm going to plug that in. 2,808, whoops. Sorry about that. That should go on the bottom. There we go. All right, I know, negative 2,808 kilojoules of energy is released for every 1 mole that is burned. This crosses out my kilojoules and would give me my number of moles. By calculating that, I take negative 9,389 divided by negative 2,808. I get from that approximately 3.344 moles of glucose must have been burned. But the question is not asking for moles, but it's asking for grams. So my final step is I need to take my number of moles and I need to convert that into grams using a mole conversion. I do this by looking up the molar mass for glucose. For every 1 mole of glucose, how many grams does that weigh? Let's go ahead and go back and find out what glucose is. The formula for glucose is C6H12O6. So it's 6 carbons plus 12 hydrogens plus 6 oxygens that gives me 180.18. And therefore, that is my molar mass. Times that by your number of moles to get you your number of grams. And my answer with correct significant figures is 602.5 grams. All right, go ahead and do this one on your own. All right, this one might be a little tricky because we're using a different delta H. First of all, I need to get my 35 grams of water into moles. So I do 35 grams divided by the molar mass of water, which is 18.02. That gives me approximately 1.94 moles. Once I have that set up, then I'm going to go ahead and relate it from moles to energy. Now, let's look at the process involved. Water is being frozen, so what delta H am I going to use? Delta H of combustion, vaporization, or fusion? Well, the problem is they don't have a delta H of freezing. But let's think, what is freezing the opposite of? It's the opposite of melting or fusion. So in this case, I'm going to use the delta H of fusion for water. The delta H of fusion for water is 6.01 kilojoules per 1 mole. So that's the amount that I put in. However, it's being frozen, not melting. So I need to change the sign and make it negative. By multiplying through, moles cancels out, and I get approximately negative 12 kilojoules of energy is released. Final one. How many grams of methanol were vaporized if 85.2 kilojoules was absorbed? Pause the video, then hit play to reveal the answer. The answer for this one is approximately 78.7 grams. Now we've looked at three types of molar enthalpy: delta H of combustion, delta H of fusion, and delta H of vaporization. The final thing I'd like to show you is how this relates to a chemical reaction. Essentially, the process is going to be the same, only now we're relating it to a balanced thermochemical equation. Let's consider the following thermochemical equation. Notice that it's balanced, states of matter, and the delta H is negative 98 kilojoules. Now I know that this reaction is exothermic, and I know that this reaction is going to release 98 kilojoules. But notice that the 98 kilojoules is always representative to how much amount is represented in the equation. By that I mean this: 98 kilojoules of energy is always going to be released for every 2 moles of benzene used, or for every 15 moles of oxygen used, or for every 12 moles of carbon dioxide produced, or for every 6 moles of water produced. In other words, the delta H is always in relation to what the amounts are as coefficients. Those coefficients represent moles. Knowing that, this is how we solve the problem. What is the amount of energy released by the combustion of 1.75 moles of benzene? Once again, always start out with what you're given. I'm given 1.75 moles. First, make sure that it's in moles. In this case, it is, so we're good to go. Now let's set it up like before. I want to go from moles to energy. All right. I know that 98 kilojoules of energy is going to be released in this reaction. But that 98 kilojoules of energy is going to be released for how many moles of benzene? Well, according to the relationship, it's for every 2 moles of benzene. And so the 2 goes on the bottom. Notice how I ignored everything else in the equation because it only told me that I had 1.75 moles of benzene, and that was it. So finally, I just multiply through. I'm going to do 1.75 times negative 98, and then divide that by 2. My approximate answer with sig figs is negative 85.8 kilojoules. And that makes sense because notice, if for every 2 moles of benzene used, I give off 98 kilojoules, it should make sense that if I use a little bit less than 2, I should get a little bit less than negative 98. And so it makes sense logically. Go ahead and try this one on your own, then I'll reveal the answer. First step in this one is to convert your 100 grams of calcium oxide into moles. The answer to that is 1.78. Now that you have your calcium oxide into moles, we know that for every 1 mole of calcium oxide, 464.8 kilojoules is needed. I multiply through and I get 828.8 kilojoules. Notice I didn't do anything with the carbon. Why? Because the problem didn't give me any value for carbon. Carbon was just in there to throw you off to see if you were paying attention. Let's do the last one. Go ahead and try this one on your own, then hit play to reveal the answer. The answer for this one is negative 114 kilojoules. This concludes the video lesson on enthalpy.